Welcome. Today's topic will be starts from this. For an infinite sequence, there are cases of convergence and divergence when n approaches to infinity as follows. Convergence, when you say convergence, sequence n converges to alpha. If n approaches to infinity, n approaches to alpha. What is alpha? Alpha is an infinite number. Whereas divergence, sequence n diverges to positive infinity. If n approaches to infinity, n approaches to either plus or minus infinity, we say this sequence n is divergence. Sequence n diverges to negative infinity. As n approaches to infinity, n also approaches to minus infinity. Then we say this an sequence n is divergent. Whereas sequence n vibrates or oscillates if an has no limit. We can say the sequence n is vibrates or oscillates. Divergence or convergence of infinite geometric sequence. Consider an infinite geometric sequence Gn, which is equal to r to the power of n, where G1 is equal to r. G1 is equal to r, which means the first term for n is equal to 1, we have r. So the first term will be r, and common ratio is r. Common ratio will be r. Let's list out some terms for this one. Gn is equal to r to the power of n. For G1, the first term G1, which is equal to, when you substitute 1 instead of n, r to the power of 1 is r, comma. For G2, which is equal to r squared, and so on. From this, the first term will be r, and the common ratio r will be G2. R is equal to G2 over G1, r squared divided by r. So the common ratio r will be, the common ratio r is r. There are cases of convergence and divergence when n approaches to infinity as follows. This geometric sequence, whether it is convergence or divergence, we have cases. Case number 1, if r is greater than 1, here r, when n approaches to infinity, this geometric sequence is divergent, that tends to infinity. For r is equal to 1, when n approaches to infinity, 1 the power of infinity is 1. So this sequence, geometric sequence, is convergent sequence. That means that this approaches to 1 as n tends to infinity. Case number 3, if absolute value of r strictly less than 1, this geometric series obviously convergent sequence that approaches to 0. Typical example, let's take for r is equal to 1 over 2. 1 over to the power of n, 1 over to the power of n is 1 over to the power of n. 1 divided by large number that approaches to 0. So this geometric sequence is convergent sequence. Number 4, for r less than or equals to minus 1, when n approaches to infinity, then Gn vibrates or limit can't exist. Doesn't exist, a limit doesn't exist. For r is equal to, for r less than or equals to minus 1, this geometric sequence limit doesn't exist. So we can say for r less than or equals to minus 1, this geometric sequence is vibrates or oscillates. Let's see particular example. Example 1, find whether the given geometric sequence diverges, converges or vibrates when n approaches to infinity. Here number A, Gn, which is equal to square root of 2 the power of n. The square root of 2, which means 1.1 1.4, something like that. So 1.4 is greater than 1. So this is divergent sequence as n approaches to infinity. This also as n approaches to infinity, this sequence approaches to infinity, so the limit doesn't exist. This means what? This sequence is divergent sequence. This is divergent. Whereas number B, here we have 2/3. 2/3 common ratio are 2/3 is less than 1. So this is obviously convergent sequence. Convergent. This approaches to 0 as n approaches to infinity. This sequence approaches to 0. So this is what? Convergent sequence, we can say. Number B is convergent. Number C, let's see number C. For as n approaches to infinity, this approaches to either plus or minus. So this is okay. This can be rewrite. Let's rewrite it like this. This is equal to minus 1 the power of n times 3 the power of n. This represent what? Minus 1 the power of n. This is oscillate representative or vibrates. So this sequence is vibrates or oscillate sequence. Let's see number A, infinity is divergent. Number B, 0. This is what? This represent convergent. Whereas number C, yes, here we have vibrates. So this is what? Vibrates or oscillates. Question example number 3. Vibrates or oscillates. Okay, let's continue. Exercise 1.18. Find whether the given geometric sequence diverge, converge or vibrates when n approaches to infinity. Okay, this one, square root of 3, 1 point something, so this is divergent, obviously. As n approaches to infinity, this tends to infinity. So this is divergent or diverges. This is divergent sequence. Divergent. Whereas number B, 3/4 common ratio arrays. 3/4 less than 1, so this is convergent. As n approaches to infinity, 3/4 the power of n approaches to 0, so this is convergent. Convergent. Let's see this one. Gn, which is equal to minus 1/2 the power of n. This approaches to 0 as n approaches to infinity. This means minus 1 the power of n over 2 the power of n. Minus 1 over 2 the power of n. This can be rewrite like this. Let's write it, which is equal to bracket minus 1 the power of n over 2 the power of n. 2 power n again, which is equal to minus 1 the power of n is plus or minus 1. Plus or minus pm plus or minus 1 over 2 the power of n. 2 power n plus or minus 1 divided by large number, this approaches to 0. So this is convergent. As n approaches to infinity, this sequence approaches to 0, so we can generalize this sequence is convergent sequence. This is convergent. Okay. Infinite series. Definition 1.5. Let n that n starts from 1 up to infinity be a sequence, and Sn be the n's partial sum, such that as n getting larger and larger, Sn goes to S, where S is a finite real number. Then we say the infinite series that n starts from 1 up to infinity an is converges, and is written as summation n starts from 1 up to infinity n is equal to S. However, if such an S doesn't exist or is infinite, we can say the infinite series n starts from 1 up to infinity n diverges. Let us consider the geometric sequence 1, 2 over 3, 4 over 9, where G1 from this given sequence, the first term will be 1, and the common ratio R is 2 over 3 divided by 1, 2 over 3. This R is less than 1. We have partial sum. Sn will be like this: G1 into 1 minus R is the power of n over 1 minus R. So after simplifying this, we get Sn, which is equal to like this. If n goes to infinity, this approaches to 0. So S infinite, as n tends to infinity, Sn approaches to 3 times 1. This approaches to 0. 3 times 1 will be 3. S infinity approaches to 3. Okay, let's see the result here. S infinity approaches to 3. Okay, let's read this one. Let us study the behavior of 2 over 3 the power of n. As n becomes larger and larger, approaching to infinity. That means as n approaches to infinity, 2 over 3 approaches to 0. Let's look it. For n, when you substitute 1 here, 2 over 3 power 1 is like this. 2 over 3 power 5 like this. 2 over 3 is the power of 10 like this. Here we have 0.1, but here 0.0. When n is equal to 2, 0.00 something like this. So from this what we understand, as n approaches to infinity, 2 over 3 is the power of n approaches to 0. That means this is 0. 1 minus 0, 1. 3 times 1 is 3. So for this geometric sequence, the infinite sum will be 3. We observe that as n becomes larger and larger, 2 over 3 the power of n becomes closer and closer to 0. Yes, we can generalize from this table. Mathematically, we say that as n becomes sufficiently large, 2 over 3 becomes sufficiently small. That means this approaches to 0, this approaches to 0. In other words, as n tends to infinity, 2 over 3 power n approaches to 0. Consequently, we find that the sum of infinitely many terms of the sequence above is S is equal to 3. Yes, here we have as n approaches to infinity, this approaches to 3. Thus, for infinite geometric sequence G1, G1R, G1R square up to infinity, if numerical value of common ratio R is between -1 and 1, not including -1 and 1, then Sn can be computed using this formula. After computing this formula, after simplifying this formula, we get this approaches to 0, this one. So the only formula will be G1 over 1 minus R. Here we have. In this case, R the power of n approaches to 0. That means if R is in between -1 and 1, this R the power of n tends to 0. G1 times 0, this is omitted. This one is omitted. Since absolute value of R less than 1 and then G1R is the power of n over 1 minus R approaches to 0, therefore Sn approaches to g1 over 1 minus r as n approaches to infinity. Symbolically, sum to infinity of infinite geometric series is denoted by s infinity. Thus, we have the formula this. Note: recall that if summation n starts from 1 up to infinity, g1 r the power of n minus 1 is equal to, when n is equal to 1, 1 minus 1, 0, the first term will be g1 plus g1 r plus g1 r square and so on, is a geometric series with first term g1 and common ratio r. Thus, then Sn can be computed using this formula. From this formula, we have different cases here. If r is in between minus 1 and 1, this approaches to 0, so the formula will be g1 over 1 minus r. Here we have. If r greater or equals to 1, the formula will be, then the series diverges or vibrates as follows. For this case, that means for if r is greater than or equals to 1, this infinite series is divergent series, not convergent. If r is equal to 1, then that means here g1 the term will be, if r is 1, g1 times r is the power of n minus 1, this is 1, so g1 times 1, g1 is constant. This approaches to this property of sigma notation. If k starts from 1 up to n, gk is constant, n times g1 when n approaches to infinity. This also approaches to infinity. If g1 greater than 0, if g1 less than 0, that means n approaches to infinity. If g1 is negative, that approaches to negative infinity. Number b, case number b, if r is different from 1, then Sn, like this with this. Then if r less than or equals to minus 1, when n approaches to infinity, then this is vibrates. For r greater than 1, as n approaches to infinity, then this infinite series either plus or minus infinity. This depends on gk value. Example 1. Determine whether the series converges or diverges. For n is equal to 1, that n starts from 1 up to infinity, 3 the power of n. Let's expand this. When n is equal to 1, we have 3, n is equal to 9 plus 27 and so on. 3 plus 9 plus 27, this is divergent to this, because common ratio r is 9 over 3, 3. 3 is greater than 1, so this is divergent. Okay. Here we have divergent. Example 2, let's see. Find the sum of the geometric series 5 minus 1, 10 over 3 plus 20 over 9 minus 40 over 27. Let's take compute the common ratio r which is equal to minus 10 over 3 divided by 5 minus 10 over 3. Let's compute it here. R is equal to minus 10 over 3 over 5. This is equal to minus 10 over 3 times 1 over 5, which is equal to minus 10 over 15 minus 10 over 15. Let's simplify this by 5 minus 2 over 3. Minus 2 over 3, after taking absolute value of this, 2 over 3 is strictly less than 1, so this is convergent geometric series, and it approaches to let's compute it, s infinity is equal to g1 will be 5 here. We have 5 times 5 over in bracket 1 minus of minus 2 over 3 which is equal to 5 over is equal to 5 over 1 plus 2 over 3, 1 plus 2 over 3, which is equal to 5 over bracket 3 times 1, 3 plus 2, 5 over 3, 5 over 3. So this is equal to 5 divided by 5 over 3, 5 times 3 over 5, 5 times 3 over 5, which is equal to 15 divided by 5, 3. So this geometric series approaches to 3. Let's see here. The answer will be here. Now let's go to exercise 1.19. Find the sum of each of the following if it exists, assuming the patterns continues as in the first few terms. Okay, let's compute number A. Here we have the first term 3. Next term 1 over 3 plus 1 over 9. The first terms we have 3. Common ratio are here we have 1 over 3. So find the sum. So here is S infinity. Question number A is S infinity is equal to G1 we have 3 times 3 over bracket 1 minus common ratio are 1 over 3, 1 minus 1 over 3, 1 minus 1 over 3 is equal to 3 over 1 minus 1 over 3, 2 over 3, 2 over 3, which is equal to this can be rewritten 3 times 3 divided by 2 over 3 times 3 over 2. So this is equal to 9 over 2. 9 over 2. This is for the sum of this geometric series. Let's see number B. Example number B. Exercise number, question number B. 1 plus 3 over 4 plus 9 over 16 plus 27 over 81. The first term you have 1. Common ratio are this divided by 1, 3 over 4. 3 over 4 is common ratio. Let's cross check it. 3 over 4 times 3 over 4, 9 over 16. 9 over 16 times 3 over 4, 3 times 9, 27. 4 times 16, 8. 4 times 16, 17. 4 times 16. 4, 6, 20, we have 24, 64, but here we have 81. So this is not geometric series. This is not geometric series. So we can take this. Doesn't exist. The sum is not exist. Number B, the sum doesn't exist because this is not, because this series is not geometric series. Okay, let's go to number C. Question number C. 1 over 5 plus 1 over 10 plus 1 over 24. Common ratio are here. 1 over 10 divided by 1 over 5, 1 over 2. 1 over 5 times 1 over 2, 1 over 10. Yes, it is correct. 1 over 10 times 1 over 2, 1 over 20. So this is correct. 1 over 2 will be R. So let's compute S infinity. number C, equation number C, S infinity is equal to the first term which 1 over 5 over 1 minus 1 over 2. This is equal to 1 over 5 over in bracket 1 minus 1 over 2, we have 1 over 2, 1 over 2. This is equal to 1 over 5 divided by 1 over 2, 1 over 5 times 2 over 1, 2 over 5. So this is the sum of this series number C will be 2 over 5. Let's see number D. Let's compute minus 1 over R, common ratio R, minus 1 over 10 divided by 1 over 5, minus 1 over 2. Minus 1 over 2, yes, it is correct. So the sum will be, for question number D, S infinity is equal to the first term 1 over 5 over in bracket 1 minus of minus 1 over 2, 1 minus 1 over 2. This is equal to 1 minus 1 over minus plus 1 plus 1 over 2, 3 over 2, 1 over 5 divided by 3 over 2 means times 2 over 3. This is equal to 1 minus plus 1 plus 1 over 2, 3 over 2, and the reciprocal of 3 over 2 is 2 over 3. 1 over 5 times 2 over 0, 1 times 2, 2 over 15, 2 over 15. So this is the sum for question number D. Let's go to question number E. 7 plus 7 over 10 plus 7 over 100 plus 7 over 1000 plus up to infinity. Let's compute common ratio R here. R is equal to this divided by 7. 7 over 10 divided by 7, 1 over 10. R will be 1 over 10, so S infinity, let's calculate it. Here S infinity is equal to the first term 7 over 1 minus R, R will be 1 over 10, 1 divided by 10. This is equal to 7 over in bracket 1 minus 1 over 10, 9 over 10, 9 over 10. This is equal to 7 divided by 9 over 10, which means 7 times 10 over 9, 70 over 9. This is the sum for this infinite geometric series. Further or infinite series. Example 1, find the sum. Let's compute this first. Let's expand it some terms for this one. This is equal to, when k is equal to 1, 5 the power of 3 minus 1, 3 minus 1 to 5 square, 25 plus, when k is equal to 2, 3 minus 2, 1, 5 the power of 1 is 5 plus, when k is equal to 3, 3 minus 3, 0, 5 the power of 0, we have 1 plus, next 4k is equal to 1, 2, 3, 4, 3 minus 4 minus 1, 5 the power of minus 1, 1 over 5, 1 over 5 plus 4k is equal to 5, 4k is equal to 5, 3 minus 5 minus 2, 5 the power of minus 2, 1 over 25, 1 over 25 plus, and so on. From this what you understand, let's compute R. The first term will be 25, common ratio R is 5 divided by 25, 1 over 5. So this for this geometric this is a geometric series. For this geometric series, the sum will be, the infinite sum will be, here is s infinity is equal to, the first term we have 25 over, in bracket common ratio r 1 over 5, that 1 over 5 is strictly less than 1, so we use this formula, g1 over 1 minus r, 25 over 1 minus 1 over 5, 1 minus 1 over 5, which is equal to 25 over, in bracket 1 minus 1 over 5, 4 over 5, 4 divided by 5, which is equal to 25 divided by 4 over 5, which means 25 times 5 over 4, 25 times 5 over 4, which is equal to 25 times 5, 125, 125 over 4. This is the infinite sum for this geometric infinite series. Let's cross check it here. So here is, it is a geometric series, yes it is, whose first term 25 and common ratio r is equal to 1 over 5, therefore the sum becomes like this, g1 over 1 minus r, r will be 1 over 5. After computing this we get 125 over 4. Okay, let's see example number 2. For this series, let's list out some term. With above example similar with above example, let's list out some term here. This is equal to, for k is equal to 1 minus 1 the power of 1 plus 1, it is positive. 2 over 3, the power of 1 is 2 over 3. The first term will be 2 over 3 plus, the next term for k is equal to 2 minus 1 the power of 2 plus 1, 3 minus 1 the power of 3 minus, so here minus 2 over 3 is the power of 2, 4 over 9, 4 over 9, next plus, here 1, 2, 3, 3 plus 1, 4, this is positive, 2 over 3 the power of 4, 16 over 81, 16 over 81, that means 2 over 3 the power of 1 to 3, sorry here, not like this, 1 to 3, 3 plus 1, 4, minus 1 the power of 4 is positive, 2 over 3 the power of 3, 2 the power of 3, 8, 8 over 3 the power of 3, 27, 8 over 27, next minus, and so let's put it like this. Now for this one, the first term will be 2 over 3, what is the common ratio r? R is equal to minus 4 over 9 divided by 2 over 3. Minus 4 over 9 divided by 2 over 3, which means minus 4 over 9 times 3 over 2, minus 2 over 3. R will be minus 2 over 3. Common ratio R is, the first term 2 over 3. Common ratio R is equal to minus 4 over 9 divided by 2 over 3. After simplifying this we get minus 2 over 3, minus 2 over 3. This absolute, let's take absolute value of this. The absolute value of this will be 2 over 3. 2 over 3 is strictly less than 1. So this is convergent geometric series. Let's compute it, the sum for this. That means S infinity. S infinity is equal to the first term 2 over 3, 2 over 3 over, in bracket 1 minus of minus 2 over 3, 1 minus of minus 2 over 3, which is equal to 2 over 3 over bracket 1 minus minus plus 1 plus 2 over 3, 3 plus 2, 5, 5 over 3, 5 over 3. After simplifying this, we get 3 by 3 is omitted, 2 over 5 is equal to 2 over 5. Let's cross check it, this one. Here is the answer will be this one. We can read from this. So this infinite series is approaches to 2 over 5. Let's go to exercise 1.20. Find the sums for each of the geometric series. Okay, let's complete this. Question number A. Okay. Let's list out some term for this one. When k is equal to 1, 1 minus 1, 0, 1 over 3 the power of 0 is 1, 5. So the first term 5, which is equal to 5 plus next for k is equal to 2. 2 minus 1, 1, 1 over 3 the power of 1 is 1 over 3, 5 times 1 over 3, 5 over 3. 5 over 3 next plus for k is equal to 3. 3 minus 1, 2, 1 over 3 the power of 2, 1 over 9, 5 over 9. 5 over 9, 5 over 9 plus and so on. Now let's complete common ratio R here. R is equal to, the common ratio R is 5 over 3 divided by 5. 5 over 3 divide 1 over 3. The common ratio R will be 1 over 3. 5 over 3 divided by 5. R is equal to 1 over 3. So from this, the first term we have 5. Again, in addition to this, 1 over 3 is strictly less than 1. So this is convergent geometric series. We can use the formula. This formula is infinity. Infinity is equal to G1. The first term 5 over in bracket 1 minus R will be 1 over 3. After simplifying this, we get 5 over 1 minus 1 over 3, 2 over 3. 2 over 3. After simplifying this, we get 5 divided by 2 over 3, which means 5 times 3 over 2, 15 over 2. The answer will be 15 over 2. So this geometric infinite series is approaches to 15 over 2. Let's complete question number B. Now let's list out some term B. Okay, for k is equal to 1, the first term 1 minus 1, 0 to the power of 1 is equal to the first term 1 plus. For k is equal to 2, 1 minus 2, minus 1 to the power of minus 1 is 1 over 2. 1 over 2 plus. For k is equal to 3, 1 minus 3 minus 2 to the power of minus 2, 1 over 4. Plus and so on. Let's put it and so on here. So for this one, let's compute it. R common ratio R is equal to 1 over 2 over 1 is 1 over 2. R will be 1 divided by 2. Now let's compute S infinity. S infinity is equal to G1 over 1 minus R. G1 is the first term 1 over bracket 1 minus 1 over 2. After simplifying this, we get the denominator part 1 minus 1 over 2 will be 1 over 2. 1 divided by 1 over 2 is 2. So this infinite series number is approaches to 2. Let's compute number C, equation number C. Let's list out some term here. For number C, let's compute it here. Number C, let's list out some term. For k is equal to 1, 1 minus 3 minus 2. 5 the power of minus 2, 1 over 25. 1 over 25 plus 4k is equal to 2. 2 minus 3 minus 1, 5 the power of minus 1 is 1 over 5. 1 over 5 plus 4k is equal to 3. 3 minus 3 0, 5 the power of 0 is 1. 1 plus minus 1. From this, let's compute r. R is equal to this divided by 1 over 25. 1 over 5 over 1 over 25. After simplifying this, we get r 1 over 5. 1 over 5. Is that 1 over 5? 1 over 5 divided by r will be 5, sorry. R will be 5. Okay, let's multiply 1 over 25 times 5, 1 over 5, yes. 1 over 5 times 5, 1. Okay, let's me add one more. 1, 2, 3, 4, when you substitute 4 here, 4 minus 3, 1, so we have 5. 5 plus and so on. So common ratio R is 5. Let's compute S infinity. S infinity is equal to, use this formula G1, use this formula G1 into, since R is greater than 1, use this formula G1 times 1 minus R is the power of n as n approaches to infinity over 1 minus r. 1 minus r. So here is S infinity is equal to G1, we have 1 over 25 here, 1 over 25 times in bracket 1 minus r will be 5, 5 is the power of n, 5 power n over 1 minus this over here 1 minus r, so we have 1 minus 5. So this is equal to 1 over 25 over minus 1 minus 4 minus 1 minus 5 minus 4. 1 over 25 times minus 4 minus 1 over 25 times 400 minus 1 over 100 times in bracket here 1 minus 5 is the power of n, 1 minus 5 power n. This is divergent. This is divergent because as n approaches to infinity, this approaches to negative infinity times negative infinity, that approaches to positive infinity. So this represents what? This infinite geometric series is divergent. Now let's go to equation number D. Equation number D. Okay, let's list out some term here. Number D. For k is equal to 1. We have, let's substitute 1 here. 1 plus 3, 4, 3 is the power of 4. 3 is the power of 4 times 2 over 3 is the power of 1 minus 2 minus 1. 3 is the power of 4. So the first term is 3 over 4 power of 4 times in bracket 2 over 3 is the power of minus 1. 2 over 3 the power of 2 minus 1 plus when you substitute 2 here instead of k2, so we have 3 over 4 power 2 plus 3 5 power 5 times 2 over 3, you have 2 over 3 power 2 minus 2 0, so 2 over 3 power 0 is 1, so we have 3 over 4 the power of 5 plus 4k is equal to 3. Let's substitute 3 here, 3 plus 3 6 5 6 and like that. So here we have 3 over 4 the power of 6 times in bracket 2 over 3 the power of 3 minus 2. Here we have 2 over 3 the power of 3 minus 2, 3 minus 2 is 1, 2 over 3 the power of 1 is 2 over 3. So times 2 over 3, here we have 2 over 3 plus, and this one, let's put it here, and this one here. So from this is equal to, again, let's rewrite this. 3 over 4 the power of 4 is 0 over 4 the power of 4 times 2 over 3 the power of minus 1, which is 0 over 2. 3 the power of 4, okay, let me write it. 3 the power of 4, 81. 81 over 4 the power of 4. 4 the power of 4, 256. 256 times here the reciprocal of 2 over 3. 2 over 3 the power of minus 1 is times the reciprocal of this 3 over 2 times 3 over 2 plus, what about here, 3 the power of 5, 3 the power of 4, we have 81. 81 times 3, 243. 243 over 4 the power of 5, let's compute it here. 4 the power of 5 is 4 power 5, which is equal to 1024. 1024. Here we have 1024 plus. Now let's compute this. 3 over 4 times 6, power 6. 3 the power of 6. 3 power 6 is equal to 729. 729 over 4 the power of 6. 4 the power of 6, 4 power 6 is equal to 4096. 4096 times, here we have 2 over 3. 2 over 3 plus, and so again, let's multiply this. This is equal to, here we have, let's multiply this. 81 times 3, 243. 243 over 256 times 2, 256 times 2 times 2 is equal to 512. 512 plus, this is as it is, 243 over 1024 plus, let's simplify this. 729 divided by 3. Let's divide 729 divided by 3. Simplifying here. This can be simplified by 3, which is equal to 243 over 4096 divided by 2. Let's simplify. 4096 divided by 2, which is equal to 2048 plus, and so on. After this, let's compute common ratio R, which is equal to this term divided by 243 over 512. R is okay. Let me write it. 243 over 512 over, in bracket here, sorry, not like this, 1024, which is equal to 243 over 512, which is equal to, let's take the reciprocal here, 243 over 1024 times the reciprocal of this is 512, 512 over 243, which is equal to, let's simplify this. This can be omitted with this one, 512 over 1024. 1024 divided by 512. Let's divide it. Sorry, 1024 divided by 512, which is equal to, so the common ratio R will be 1 over 2. After simplifying this, we get 1 over 2. Let's cross check it here. The numerator part, 243, this is fixed. So 512 times 2, 1024, 1024 times 2, 2048. So the common ratio R 1 over 2 will be correct. Now let's compute S infinity. S infinity is equal to, since R is less than 1, we use this formula, J1 over 1 minus R. So let's substitute for J1. Okay, let me write the formula, J1 over 1 minus R. So this is equal to, instead of J1, we have to substitute 243 over 512 over, let's put it in bracket like this, in bracket here, 1 minus 1 over 2, which is equal to 243 over 512 product with 1 minus 1 over 2, sorry, in bracket, let's put it here, over this 1 minus 1 over 2 is 1 over 2. 1 over 2. So this can be rewrite, which is equal to, this divided by 1 over 2 is this times the reciprocal of 1 over 2 is 2. So 243 over 512 times 2. 243 over 512 times 2 over 1, 2. So this is equal to 243 times 2, 486. 486 over 512. This is the sum of the infinite series. Question number B. For this infinite geometric series, the sum will be 486 over 512. This is the infinite sum. So we can simplify this. this is equal to, okay, let's divide this by 243 over 512 divided by 256. So this is a simplified answer. Okay, let's go to the next subtopic. Recursive decimals. Recurring or repeating decimals are rational numbers or fractions whose representation as a decimal contain a pattern of digits that repeats indefinitely after decimal point. The decimal that starts the recurring cycle immediately after the decimal point are called purely recurring decimals. Purely recurring decimals are converted to an irreducible fraction whose prime factors in the denominator can only be the prime numbers other than 2 or 5. That is, the prime numbers from the sequence 3, 7 and so on. The decimals that have some extra digits before the repeating sequence of digits are called the mixed recurring decimals. The repeating sequence may consist of just one digit or of any finite number of digits. The number of digits in the repeating pattern is called the period. Mixed recurring decimals are converted to an irreducible fraction whose decimal denominator is a product of 2's and or 5's besides the prime numbers from the sequence 3, 7, 11, 30, 17, 19 and so on. All recurring decimals are infinite decimals. Converting purely recurring decimals to fraction. Example 1. Convert the purely recurring decimal 0.3 to fraction. Let's convert this to fraction. So 0.3 dot here, the repeated term will be 3. So this can be expressed like this. You can write it. This is equal to 0.333 and so on. So this can be rewritten as a geometric series like this. This is equal to the first term 3 over 10. 3 over 10 is 0.3. Next plus 3 over 100. 3 over 100 is 0.03. Here we have 0.3. Here 0.03. When we add these two, we have 0.33 plus 3 over 1000 plus and so. This 3 over 1000 is 0.003. After adding this all, we get 0.333. So from this we have the first term 3 over 10. Common ratio R here is 1 over 10. The numerator part we have the same term here 333. The denominator part here we have 10 times 10, 100 times 10, 1000. So the common ratio R will be 1 over 10. So this is equal to the sum of this. Since this is geometric series, we can use the formula, and R will be 1 over 10, 1 over 10 less than 1. We can use formula J1 over 1 minus R. So J1 3 over 10. 3 over 10 over here 1 minus 1 over 10, which is equal to 3 over 10 1 minus 1 over 10, 9 over 10 in bracket 9 over 10, which is equal to, let's simplify this, 3 over 10 divided by 9 over 10, which means 10 by 10 is omitted, 3 over 9, that is 1 over 3. So this fraction form, this decimal number form can be expressed as a fraction like this. 0.3 dot is equal to 1/3. This is the fraction form. This given decimal number can be expressed as a fraction form as 1/3 like this. Let's cross check it here. Yes, here we have. So the answer common G, the first term is 3/10, R 1/10, yes. So since R is less than 1, that is 1/10 is less than 1, so the sum will be 1/3. This 1/3 is the fraction form of this decimal number. So today's topic, let's stop it here.